In section 9.3, we want to be able to make confidence intervals for the population variance and the population standard deviation, right? They kind of go hand in hand because one is just the square of the other. So if you made a confidence interval for one, you've basically made the other one as well. But we did that for proportions P in section 9.1. We did it for mu in section 9.2, but there's a big problem. And that is because variance is squared, and then the square root of that is the standard deviation. Neither one of them can ever be negative. But the z and the t distributions were negative. Let me go back to them real quickly so you can see them. Here you can see them in section 9.2. We had drawn a z curve and a t curve, and they're both symmetric around 0. Well, first of all, they're both symmetric. And second of all, they both have 0 in the center, which means half of the values on the left side, all the values on the left side, are negative, whereas half of them are positive. That's not going to work for us because the variance was squared, we're never going to have that left-hand side. It's never going to happen. So we need to be able to come up with a new curve that won't look like the z or the t curves that will serve our purposes. And that's what the chi-square curve does. So let me go back to section 9.3. There we have it. So we need a new distribution called the chi-square distribution. The chi-square distribution has its own its own issues, and we're going to learn what they are because we're going to use distribution in chapters 9 and 10 quite a bit. Okay. All right, so it's you can use this distribution when you're taking a simple random sample of size n from a population that is normally distributed. So the curve comes from the normal distribution, but it isn't exactly the normal distribution. So you have to have the distribution of the population as normal before you can even make the chi-square curve. And the chi-square curve is essentially sort of like squaring the normal curve, right? It takes those values that could be negative and it makes them all positive. And that's because when you look at the chi-square statistic in here, you can see everything is squared in there. That's because if everything's squared, you're never going to have negatives. All right, it's going to have degrees of freedom n minus 1, so it's actually more like a t-curve squared, right? So you're going to have degrees of freedom. That means just like the t-curve, you're going to have infinitely many different curves, and you're going to have to be able to find a whole bunch of them. However, unlike the t-curve, you will not be able to use a calculator. You're going to have to use the tables. All right, so what are the properties of the chi-square distribution? Well, let's look at some pictures of them first of all. These are two of the infinitely many possible chi-square curves. And by the way, that's chi with a hard k sound as opposed to chi, which is a t. Chi is C-H-A-I. It's not the same thing at all, right? Chi is a Greek letter. It looks sort of like an X when you write it out in Greek. And I think I have that up here, right here. That's the Greek symbol right there. It looks like an X, but it's actually chi. It's kind of an italicized X. So you can see that for both of these curves, they're never negative. They actually stop at 0. See that right there? The curve actually has an end point over there on the left side. It stops right then and there. Right. The distributions, all of them are not symmetric. None of them are. They're all actually skewed right when you look at them. Right. So they're all skewed right. It's just to varying degrees, depending on something else which we're about to see. Okay. The area under the entire curve is 1. Well, of course, because it's a probability distribution, the area under the entire curve has to be 1. Right? It has to be. Otherwise, you wouldn't be able to get probabilities out of it, and it would no longer serve your purpose as a probability distribution. All right, the x-axis is a horizontal asymptote, but only on the right side. Right? So only on the right side is it a horizontal asymptote, because on the left it actually stops at 0, 0. It stops at the origin. That's what these points are hitting at 0, 0. But over on the right, it surfboards along that x-axis over here. So that's the horizontal asymptote. All right, next. And then as sample size increases, the chi-square density curve becomes closer and closer to the z distribution. Just like we saw with the t curves, the bigger your sample, the more normal, quote unquote, it's going to look. Now, grant you, degrees of freedom of 10 is not great. It's still skewed right. But do you see how it looks more normal than that tall, jagged one for the degrees of freedom of 5, right? And that would keep going on more and more, right? The larger your sample, the larger your degrees of freedom. The larger your degrees of freedom, the more normal the distribution is. It never really gets fully normal. Well, it does if you take an infinite limit, but for our purposes, we're going to say it's skewed right, and then we're going to say it's becoming more like the normal curve as n gets larger. All right, before we move on to go find critical values, let's sum up real quickly. The chi-square distribution is the one we have to use for variance and standard deviation because neither one of those can ever be negative. All right, the chi-square distribution is funky. It doesn't look like the other curves you've worked with so far. It's not symmetric, it's skewed right. It does have degrees of freedom, just like the t-curve, and then the larger that degrees of freedom, the larger your sample size, the more, quote, normal it looks. It does have a vertical asymptote, but only on the high side, and it hits at the origin.